So now let's move on and talk about color. So we just spent a lot of time talking about arranging data in space for tables and networks and spatial data. Now let's talk about color. There's other visual channels as well that we won't have time to cover in this tutorial. So the first rule of color is don't talk about color. Color is incredibly confusing if we treat this as a monolithic channel, because in fact, it's not. What we need to do is decompose color into 3 channels: luminance, saturation, and hue. So 2 of these are magnitude channels that can show ordered attributes. So both luminance and saturation, we can think of luminance like black to white, saturation like the vibrancy of a color. These are things that have an implicit perceptual order. If I put someone in a room and I say, here's a dark gray and a black and a white and a light gray paint chip, please put them in order, I bet the 2 different people will put them in the same order every time. But hue is an identity channel. It can be very well suited for showing categorical attributes. But if I put 2 different people in a room and I gave them a blue chip and a green chip and a red chip and a yellow chip and an orange chip, and I said, put these in order, I don't know what order they would do, and I would not bet $1 million that it would be the same order. So it's not perceptually ordered the same way that the other 2 channels are. So luminance, saturation, and hue is a perceptually oriented color space with 3 channels. Some of you who've done more web programming or computer graphics might be aware of RGB as another color space. It is 3 channels, but it's a very different hardware-oriented color space as opposed to a perceptually oriented one. So this one is much more well suited for thinking about visual encoding. Now with luminance, a key thing to know is this is what the human visual system needs to detect edges. The only way you see fine-grained detail is through luminance contrast. That means you need that to make sure the text is legible. Keep that in mind. This is a really evocative picture from Marine Stone where we've got an apple orchard decomposed into the luminance channel and then all the other color information. And notice how all of the crisp detail is in the luminance channel and the color is much more hazy and blurry and difficult to see crisp edges with. Now, speaking of color spaces, there are, in addition to RGB and a lot of color pickers, there's many that give you HLS or HSV. Be aware that that L of lightness is not the same as true luminance, which is technically called L star, although we're not going to get into that in this tutorial. But do be aware that if you look at colors in RGB, you're going to see that some like blue are really much darker and some like yellow and green are much lighter. Be aware that these will all be the same lightness value in an HLS color space, even though they have very different true luminance values. There are very few tools that actually do allow using true luminance, unfortunately. If visualization takes over the world, as it should, then maybe we'll see more ability to actually use a true luminance picker in other contexts. So let's talk about the use of color to show categorical information. A key thing is, how many bins can you use? And the answer is fewer than you want in general. So here's an example out of a bioinformatics paper where there was an attempt to try to use 20 different colors. And in fact, when you look at essentially the right side, which is the mouse genome, there's 1 color per chromosome, and it seems perfectly reasonable. Even though the distinctions between the greens are pretty subtle, you can see in the legend, you can distinguish between them. We can understand very fine gradations of things that are side by side, because in fact, our perceptual system is built on relative comparisons rather than absolute ones. The problem comes on the left side, where we look at the human genome with the chromosomes color-coded by where things appeared on the mouse genome. Now, things are much trickier. We can look in the top left, we've got tan and then green and brown and white and reddish, and well, that's green again. I think we've already got that. There's a darker blue. Okay, on chromosome 2, there's a light blue, a cyan, a purple, some sort of weird not quite green. Wait, we've already seen the other green, already seen the red, already seen the orange. It's getting very hard to distinguish colors, and I haven't even run out of fingers yet, but we're nowhere near the 20 colors. The problem is that all those difficult shades of green on the right side, we can't distinguish them when they're tiny little non-contiguous blocks. So fundamentally, we have quite limited abilities to distinguish non-contiguous small regions. A very safe rule of thumb would be from 6 to 12 bins. Keep in mind that includes the background and maybe a highlight color and a neutral color. So it's quite tricky. A lot of people are tempted to push categorical color beyond what it's capable of. A lot of understanding the visualization design space, both through this tutorial a bit and through doing further reading, is to understand alternative options of using different channels, not just trying to rely on categorical color. There's different strategies, so you don't have to have the entire burden on the shoulders of categorical color. People are very tempted to go and push it far more than what we can really resolve. The other very common mistake with color is to think that rainbows are good to use for ordered attributes. It's not a good choice for default. We've already talked about the problem that it's perceptually not ordered. Moreover, it's not even perceptually linear. So consider two different same-size portions of this color ramp. On the left side, we've got, we can tell there's sort of a darkish red-orange, and then a pretty bright orange, and then a yellow, maybe even a tiny bit of green. The same size ramp in the green section, all we can see is green. It all looks green. And so that means that attribute values that happen to fall into one part of it are going to be distinguishable, and that happen to fall into another part, even if they vary the same amount, are not going to be distinguishable at all. That's a serious problem with the rainbow color map. It has to do with the spectral sensitivity of the human eye to different wavelengths. So even though it's physics, which is that yes, sunlight through a prism will in fact show us a rainbow, and that is a fact of physics, the biology of our perception does not make rainbow color actually necessarily such a good choice. Now, it's not that there's no good things about it. It's a good way to see very fine-grained structure that is very visible and also very nameable. In these pictures, you can talk about the orange part and the green part and the cyan part pretty crisply and clearly. However, particularly for that image on the bottom, it's pretty hard to see what's going on. So what are some alternatives? If what you want to see is not fine-grained structure, but large-scale structure, then a different kind of color ramp, like we see on the right here, where we're going from purple through a neutral gray towards fully saturated yellow, now we're much more able to see large-scale structure. Moreover, speaking of making things visible, if we try to be very careful about the construction of a color ramp, we can even shed light on this mysterious thing on the left. This is actually the coastline of Florida, but there was no way to tell because crucial information right at the 0 point was in the really hard to distinguish yellow-green section. With a carefully designed color map that has a very distinguishable boundary at the 0 point, and so we've got some divergence and some segmentation, we can see that much more clearly. And then things, notice how things are getting darker and darker as it goes deeper in sea levels, and then brighter and brighter as we get towards high altitudes. This is actually an example of a color ramp that's carefully designed so that even as you have multiple hues, the luminance is monotonically increasing in one direction and decreasing in the other. This design principle was well used in things like the Viridis color system. Let's take a look at that. Both Viridis and Magma are custom designed color palettes that they have monotonically increasing luminance as you go, which is not at all true for many of the other defaults. They're perceptually uniform. They're even colorblind safe. They're incorporated into many tool packages like R and Python and D3. And you can see from these two color ramps that we really are able to have color nameability and this crucial thing of using the luminance ordering so that you have both nameable hues and ordered luminance. I'll mention one more thing before we leave the rainbow, which is not all rainbows are bad. Rainbows are perfectly good for categorical data. If you want to have a segmented color map, then for categorical data, you actually want the very bright and vibrant colors. You want to have as high saturation as possible to have those little small non-contiguous areas be as distinguishable as possible. So rainbows are great for categorical data. They're a pretty poor choice for ordered data in general. So to try to wrap up thinking about color maps into one big continuous context, we can think about color as being used either categorically or for ordered data. It can be sequential or diverging. We can see a few color maps there of min to max versus 0 point going outward. There's even the binary case of just having two values. Now, what else should we think about? all of those previous examples were single univariate color maps. What if we try to show things two different attributes using color? People have designed these so-called bivariate color maps where some of them are much more dangerous than others. If you simply say, well, I want some, say, categorically different data, and then I'm going to have a fully saturated version and a less saturated version. So it's multiple categorical levels in one direction, but only two binary levels in the other direction. That's that one up on top. That's actually pretty safe. Things get trickier if you're trying to have multiple levels in both the directions. So whether it's diverging or diverging sequential, although a lot of people do want to use them, people have gone to great care to carefully design them, a lot of people do end up finding them confusing. There's been a lot of empirical research about some of the challenges of interpretability with bivariate color maps. So be careful, there be dragons there. So think with categorical color, 6 to 12 bins, and that's if people have normal color vision. We don't have time to get into color blindness in this tutorial, but it's a major, major topic affecting 8% of men. What about luminance and saturation? It's probably safe to think about maybe 3 or 4 bins max in terms of, again, if there's non-contiguous separated regions, you really don't have that many discriminable levels. Be aware also that size deeply affects the visual salience of color. You need very high saturation for small regions, and conversely, if you have really large regions of color, think about having desaturated colors so that you do not blow out people's eyes. So that was just a quick drop in the bucket of all of the things that there are to know about color. As always, we've got some further reading, and then we'll move on to questions and the next segment.